I'm a member of the ROCSAT team for Temple University. We're Team 15, and my team members are Brittany, Dave, and Joe, and our advisor is Dr. Helferty. And so, like I mentioned, the program we're doing is ROCSAT-C. This is actually a model of the rocket that the payload section of the rocket that we're going to be flying on, and it is NASA's Terrier Improved Orion rocket, and it's a two-burn phase rocket that travels at speeds of up to just above Mach 4. So what I'll be talking about today is our team structure and just our general mission, the testing that we've done on the electrical system, and the successes and challenges we've had in designing and manufacturing the mechanical part. So, like I said before, Joe, Dave, Brittany, and myself. Further back in Senior Design 1, we had more clearly defined roles of exactly what each team member was doing. But as it came towards the end, those kind of boundaries overlapped more and more, which has been nice because it really makes sure that our hardware and our software interface properly and that we're working close together. So our mission overview, the general idea is to collect samples throughout the atmosphere throughout a range of altitudes in order to get experimental data to confirm or challenge the current models that they have for the gas content in the atmosphere. And the reason that's important is because it has a huge impact on the air pollution forecasts, which therefore have a big impact on emissions controls laws. And so we're hoping to get 28 cartridges full of air that is a sufficient volume for mass spectrometer analysis, which will be 50 microliters at standard temperature and pressure. And so we figured out the properties of air at each sample altitude, and we will collect that same volume, that same mass, excuse me. So our general approach, we have several different subsystems. This will make sense when I pull up the next couple slides. So basically we have several 28 cartridges around the track, and it moves into place and then connects so we can take in air from the outside and we pump it in. And then it disengages and rotates into place. And so we do that through these subsystems. So this is our overall system. Like I said, this right here is the rotating track, and you can see these cartridges which have Schrader core valves in them. So they're completely airtight. I think to about 65 psi outside pressure is when they'll depress. But we actually depress them using this solenoid here, which is this solenoid here with the T attachment on it. And again, I'll explain that in a later slide, but it basically creates a tight seal with the cartridge and depresses the core, so airflow can come in here through tubing and into the cartridge. And so this is our model, and it's pretty much the same thing as the last one, just a little bit brighter so you can see what's going on. So like I said, what happens is this track rotates the cartridges into place. Once they're in place, that solenoid is activated, the T attachment moves up, creates a seal. Airflow is then allowed to go in through the T attachment. It is attached to the pump. You can't really see it in this view. But tubing from our dynamic pressure port goes into the pump. It is then pumped to the valve, which has been switched to allow airflow to go into the T attachment and therefore into the cartridge. And when it's switched, when the valve switches back, the pump stays on, so it's just completely constant. But when the valve moves, it redirects flow back into the static pressure port, which the pressure there is already lower than the dynamic pressure port anyhow. And so that ensures that we don't have any sample contamination or any like residual air from previous altitudes when we're taking our next sample. And so system update. Finalizing our parts took a whole lot longer than expected. And that was especially difficult for our pump just because we were having trouble understanding the gauge pressure at different altitudes because it always references atmospheric pressure, which kind of becomes funny when you're changing altitude. So that was kind of a matter of just confirming that we understood the technical specifications of our products, of the products that we ordered completely. We have also finished all of our software and electrical integration. All of our subsystems worked individually, and then we added them together piece by piece until we have the entire system working. Major changes, we were initially going to use an onboard optical spectrometer to measure the wavelength of light coming in throughout the entire flight. But we did away with that because that would have been another considerable amount of work on top of what we had already done. The pump is reintroduced. I'll get into that in the next slide. And we also used an Arduino Mega. Before we were going to use two separate Arduino Unos. And the reason for that was we needed more pulse width modulation pins. And so we just went with the Mega instead because that has as many as we need. And also we changed to using two servo motors to help, one to help retract the solenoid, because it's not a push-pull solenoid, because that would have generated too much heat throughout the flight because you got to feed voltage to it the entire time. And a spring to retract it wouldn't have worked either because the tolerance is so small that the T attachment would have just been oscillating throughout the flight. And so we used one servo to turn it down, turn the solenoid down, and another one to lock our track into place during periods of angular acceleration, which happens, the rocket usually spins at about 5.6 hertz, but then when it goes through its second burn, it switches to about 1.6. And so that immediate change, and also on takeoff, causes a torque on the motor, and so we need something to hold it there, and you'll see that later on as well. Our main concern is just making sure that motor aligns properly, and if that happens, we'll be able to. Space is not as big of a concern as it initially was, mainly just because we have, I would say, 95% of our parts placed in the model, and it works great. So the mechanical subsystem. So right here, this is kind of a dense slide. So, like I said before, it's traveling it over. It's supersonic. It's traveling supersonic. So you see in zone 1, your Mach number is going to be greater than 1. And so what that means when you have a perturbation in the flow is right here, you're going to have a conical shock wave. And what that means is that there's going to be an energy release, and in zone 1 and zone 2, you're going to have drastically different properties of air as far as pressure, density, temperature, things like that. And so that's turned parallel to the nose cone. And then it expands back around here because there's a lower pressure here. So again, you have a new set of properties. And then, as you can see right here, okay, so this is where our cartridge is going to, or our canister, excuse me, is going to be, and right here is where we're collecting air from. This, like zoomed in here, is this right there. And so this is pretty small. It's less than an inch, but it's enough to also perturb the flow. So you get another conical shock, again changing the properties of air. And so we had to do a pretty hefty analysis to get from using like the standard atmospheric models and using flight radar data from a previous flight to calculate all of the properties of air that we would experience, so we would know how long we would have to pump air into each cartridge because it changes with altitude. And also on the other side, you can just see a 3D model of the airports. And so, like I said, this right here is what we previously thought the pressure was going to be, but oh no, this one is the one we thought the pressure was previously going to be. But with the addition of that final shock wave on the dynamic pressure port, it's actually much lower. And this is a big deal because with that shock wave, we would only be able to collect samples up until 20 kilometers. But before, we thought we were going to be able to collect up to 35. And so we need something to compensate this gap, because we need to fill our cartridges to this value right here, this red line. And so we reintroduced the pump. And this is kind of just the last slide put in a different way, but also with the introduction of the pump. And so we figured out the time collection window we would need for each sample as it goes up. And you can see once it gets to like pretty much here, that's already at 5 seconds. And if you think 5 seconds when you're traveling supersonic, you're already another 10 kilometers away. So it's really restricted to less than 35 kilometers is the zone that we picked. And also you can see right here, that's just, we scheduled out all of the cartridges throughout the flight to make sure that we had time, because our collection window is pretty small. And we integrated that into the software, and it's based on this timing. So the T-attachment design took a little bit longer than expected. That's probably our biggest manufacturing challenge. It's currently being made in the Barton manufacturing, and we should be picking it up tomorrow. The polycarbonate layers still have to be manufactured, but we're doing that in the CNC machine, and that should happen very quickly. The only reason we've been holding off on that is we need to place all the fasteners throughout the model. And once we do that, it's just a matter of sending the information. We're using standard hex head screws. We made 3D mounts actually for most of the components in there. And the one other thing we have to do is manufacture the solenoid mount. And the only reason that that's special or it matters is because it turns out the solenoid needs a heat sink. Again, because I said voltage is being sent to it, so it heats up a lot, and the aluminum will help dissipate that heat. So this is what I was talking about. The one servo motor is used to retract the solenoid. So let's start down here. You can see this is in the engaged position, and this is completely off. So whenever the solenoid turns on, like, it just pushes it up. This is a special clevis pin that we ordered, and it helps this, which is also 3D printed, attach directly to the T attachment. And so when it pushes up, it makes the tight seal, and when it's up there and the solenoid disengages, the solenoid is turned off, then the servo turns on and is able to pull it back. So this is a cross section of the T attachment. Like I said before, you can see the little depressor in there that allows airflow to happen, and there's a U-ring seal that's fixed on there with special adhesive that we got that can bond aluminum to that specific rubber. And right here, that's actually going to be an 1/8" MPT connector that our tubing from the valve is going to be connected to. So this is actually a picture of part of our rotating track. You can see there's a little hub here which attaches it to the shaft, and this is our stepper motor. What's not pictured here is there's sectional pieces that you can clamp these, and this is a cartridge that we actually made. This sets in the little, you can see the arcs there, and then you screw in radial screws, like you can see down here, the screw holes, and that clamps everything in from outside. So this is our locking attachment, which it's a little difficult to see, but as you can see in this past slide, you see the arms going outward on each for the track. You can see that on our 7th cartridge, because we're only able to collect 6 on the ascent because it happens so quickly. It's something like I think like 30 seconds at the most. We're able to collect, and once we've hit that one, then we send this up. It locks the track into place so that the stepper motor doesn't hop out of step, and we make sure that that tolerance is tight enough so that the arc, when you move it from side to side, is smaller than the step size of the motor, which is 1.8 degrees. So like I said before, T attachment would be most difficult. Threading the cartridges and getting the valve cores in there is a little tedious, but most of that's done, and we just need to manufacture the polycarbonate and the mount for the solenoid, which should be able to happen pretty quickly. Additionally, we have all the connectors. there's something like 15 or 20 different connectors that we have for all the tubing going into the valves, going into the pumps, going into the ports. We're using ball-ended thrust screws to help support the track, so when the solenoid pushes on it, there isn't any sort of force imbalance, and the supporting columns have been placed throughout the pump. So, electrical subsystem. In general, what's going to happen is the same loop, but right at the beginning of launch, we interface with Wallops and the Wallops Flight Facility, and they give us a 2-minute countdown. At the end of that 2 minutes, they activate our system, but we wait until we sense, with our accelerometer that's on board, we wait until we sense, I think it's like a 5G threshold in the longitudinal direction, and once that occurs, then we initialize our system, and that just confirms that the launch happens. At that time, our locking arm is in the engaged position, because you start out stationary, and then within milliseconds you're going at 5.6 hertz, so you need something to counter that torque. And then so that retracts, and our first sample is taken at 10 seconds. And so what happens is the solenoid goes up, like I said, air flows in, because the valve is allowed to, the valve makes airflow from the dynamic pressure port into the cartridges, and the pump is on this whole time. And then afterwards, the valve switches it, so from the dynamic pressure port, it flows back out of the static pressure port, and the solenoid is retracted, and then the stepper motor rotates the next cartridge into position. And that happens until all of the cartridges are full. So just a quick status update for the electrical side. All of our subsystems have been tested individually, and they were actually tested. One discrepancy is that they were tested using an Arduino Uno instead of our Arduino Mega. But when we integrated all of the subsystems together, we tested it using the Mega, and it is completely functional with that. The thing that we still have to do is get the printed circuit boards together and do just a full flight simulation with the time schedule that was up there before for the cartridges. So this is our power budget for the solenoid circuit. And so what's important to note here is the valve solenoid, which is a pretty little solenoid. But this and the air injection solenoid by far consume the most power out of any of our components, and they're only operating for 60 seconds apiece. But I'll move on to the next slide, and you'll see that that's a pretty hefty amount. And this is with our 14.8 battery, which is the biggest battery we have. So this is for the motor and pump. If you notice the required power, it's nothing. It's like 30% of the other one, less than that even. So we're doing a 7.4 volt battery to power that. These are on separate power circuits. And lastly, we have an Arduino that's just powered by a 9-volt battery. And also these, just the servos, they're really small, and the accelerometer. So like I said, the individual subsystem testing is done. Something that we are a little concerned with is the heat generation from the transistors for the H-bridge, which is the stepper motor controller, and from the solenoid, but that should be taken care of by two different heat sinks. One is the mount for the solenoid, and the other one is like an aluminum pin attachment for the H-bridge. And the responsiveness of the accelerometer. We were testing different threshold values in the code, but I think we have to pick what's going to be the right longitudinal force to wait for before activating, because it has to happen. Since everything's a function of time, it needs to happen like on schedule. And so I think it should be safe to say it's a 5G load, because In the longitudinal axis of this rocket, you can get impulses of up to 25 Gs, and so that's pretty heavy. But the full subsystem integration was a success. So we want to test all of the power, current, and voltage levels of all of our systems as they're operating throughout the flight. We want to test the current limiting resistors and just make sure that our power distribution works as we think it will. So far, all of our testing has been done using like a stationary power supply. So you can see here, like, yeah, you'll notice that one's still an Arduino, but this is our stepper motor and pump circuit. So this is the pump right here, the Arduino, and I think, is that the accelerometer? Is that the accelerometer? No, it's the H-bridge. Okay, this is the H-bridge here. And you got your stepper motor down here. So this is our SD card being powered by the Uno, and it's able to read and write successfully. That's the accelerometer. And so this is just us making sure the servos rotate to the degree that we want them to. This is actually the attachment, not this little line thing. But we just want to prove that it will rotate 90 degrees like it should. This is our total electrical system, a little chaotic, but servo here, SD card. Notice that this one's a little bit longer than the previous microprocessors. That's the Mega. The solenoid is here. This is the track hooked up to the stepper motor. This is your valve. This is another servo, and I think that covers it, except for the H-bridge and accelerometer. So risk assessment. We did this before, and things have changed a lot since then. So the thing that we're most concerned about is if the stepper motor gets shifted out of step, and what we can do to mitigate that would be to use a higher holding torque stepper motor, which I think is something we're going to do before this actually gets launched. But the design right now, I think, is safe as far as all of these other considerations, because the solenoid overheating is taken care of from the mount. The T-attachment, we're concerned if it doesn't interface correctly, but again, that's kind of based on this, because we have to make sure the alignment is good. I think the interfacing is going to be fine, and the U-cup is designed in such a way that when it pushes up, the seal gets tighter and tighter on the cartridge the further up it goes. We're concerned if the supports or mounts fail. We're going through 10G vibrational testing before this is even on the rocket, so I think this is something that we'll be able to test, and based on stress simulations that last year's team did, I think we'll be fine on that. If the valve doesn't operate properly, again, it's just a solenoid, and we've tested it several times. We think that should be fine. Accelerometer does not activate a system. Again, that's based upon the threshold value, and just making sure all the connections are secure. I think that's safe. And if the microprocessor just fails. And actually, on that note, I was concerned a little bit about the accelerometer being too close to either of the solenoids, because I don't want the magnetic field to interfere with anything on the microprocessor. So we'll make sure that's far enough away from those things that it's not a factor. So this is our schedule until launch. It's kind of monotonous to go through, but basically we just are going to finish our prototype by next Thursday. As it gets closer to the launch, we have weekly teleconferences with our Colorado Space Grant Consortium, who's our interface with NASA. We have teleconferences with her, so she makes sure we're on track, and we'll be speaking with Dr. Helferty to make sure everything's in place for the launch. Something that should be included in there additionally would be changing the motor. We're going to do a few more torque tests on the motor, but just to ensure that our alignment is 100%, I think we might end up going with a larger holding torque stepper motor. Lessons learned, that the parts will always take longer to order than expected, for our team at least. Small tolerances are really difficult to deal with, not only in manufacturing, but when you're trying to design things like designing different attachments when you have very limited space is really difficult. And also, we not only setting deadlines for ourselves, but really making action plans and sticking to them is very important. So conclusions is we have a few more things we need to manufacture. Like I said, the T attachment should be done by tomorrow. The polycarbonate's going to happen early next week. All of our electrical testing is done. We ordered the batteries, and I think we may have received them before. And so we need to test it with all of those batteries, and we'll assemble it, which should happen very quickly based upon everything in the SolidWorks assembly. Any questions?
Video.
Oh, right. Video.
It's on YouTube?
Yes.
Yeah. How'd you know?
Why not? Oh, no, that's not on YouTube.
It is. It's just ridiculous.
I'm a professional. I never
Questions?
Are there any questions in the meantime?
Being a mechanical engineer, I don't know, I don't have much experience with breadboards, but does vibration or anything on this breadboard have any factor on the wires coming loose?
It's going to be on a printed circuit board. Those were just for
Okay.
testing. That's one of the things that we mentioned before is that needs to happen in the next.
Saw Dr. Slides was going to have a heart attack when he saw that spaghetti mess of
Why are
wires.
we making it?
It's all it's not a spaghetti mess. It's all going to be on a PCB and things. And actually, they do go through a 10G test down at Wild. They do a spin test and a vibration test.
I do have a couple of questions. I mean,
Let them see, show the video, and then you can.
I'm curious why you collect some samples on the ascent versus the descent, because unless it's like a timing issue, because
It's
you collect them all.
timing purely.
Okay, because that way you can avoid the effects of supersonic flight.
Yeah, we're going like Mach 3, Mach 4, and so from the time that our available collection window is from 5 kilometers to 35 kilometers, based on the pressures that we're able to overcome and the timing. So when we go from 5 to 35 on the ascent, that happens like extremely fast, like 20 to 30 seconds. It happens, and on the ascent, it's no acceleration from any thrust. It's just gravity pulling us back down, and so we're able to collect many more samples. And then a chute opens. I think we collect all of our samples before the parachute opens. Actually, yeah, I know we do. But that's the whole reason.
Where's your parachute deploying at?
15 kilometers.
So you'll be sampling during that phase also?
Yeah, well, no, our goal was to get the higher altitude samples because those are harder to get to by balloon, and since the fact that we're on a sounding rocket, it would be ideal to get the higher samples.
I'm sorry, one more quick question. So your module actually deploys separately from the rocket, so it parachutes down by side. We're still attached to the rocket.
It's attached, and then it's completely self-contained, and the valves and all the ports are completely shut off, and so it parachutes down, the rocket is retrieved, and our payload is handed back to us, and then we have 28 full cartridges.
Okay.
Now, the 2 solid rocket boosters are gone.
Okay.
Yeah.
Lose them. They're gone. It's just the payload is what comes back.
Yeah, the section of the rocket that you saw on the first thing.
Okay.
So yeah, let me play this video. Hopefully the audio is pretty good. It's Dave explaining the testing of our system.
This is a whole system integration test for all of our different subsystems. Initially, the servo motor is going to lock the track into place during launch and it'll wait for a signal from the accelerometer to detect movement from the rocket. So once the accelerometer detects the movement, the servo is going to unlock the track and the timestamp is recorded. Now the system is going to be operating continuously now. Initially, the solenoid is going to connect. The valve is going to open.